Like they are doing this, it works.
Yeah, okay.
Wait.
Thank you. Hello, everyone. So my name is Drew Backhouse. I'm a second-year PhD student at King's College London, and I work on finite volume effects in quantum field theory. And I'm going to talk to you about a project working with my collaborators Jean-Alexandre and Sylvia Pla, who's here today, about trying to dynamically generate a non-singular cosmological bounce using tunneling in quantum field theory. So let's start by defining the null energy condition. So if I consider a perfect fluid of pressure P and density rho with an equation of state P equals omega rho, then the null energy condition becomes a statement that the sum of your energy density and your pressure is greater than or equal to 0. So for fluids that we are aware of, such as matter and radiation, with an equation of state omega is greater than -1, indeed, this is satisfied. Also for dark energy, where the equation of state is exactly rho plus P equals 0, it's exactly satisfied. However, we can think of a regime of omega less than -1, and in this regime, the null energy condition is violated. And this is known as phantom dark energy. So what is interesting about this stuff? Well, if I put these fluids into the Friedmann equations and plot them, as you know, matter and radiation has this power law expansion, dark energy has this exponential expansion, but this phantom dark energy, due to having a minus sign up in its exponents, actually has an even faster acceleration. So this will cause your space-time to expand even faster than an exponential expansion of dark energy. And why is this useful? Well, as we've heard about a little bit today, there's another model to solving the problems of Big Bang cosmology known as the cosmological bounce. However, dark energy alone, so what is the bounce? The bounce is where you start with an initially contracting universe that bounces and transitions into an expanding one. However, dark energy alone is not sufficient to avoid the universe collapsing into a singularity. However, this phantom dark energy is sufficiently strong to transition us into an expanding universe. This is also consistent with the Hawking and Penrose singularity theorems that state that in order to avoid an initial singularity, you need to violate the null energy condition. So I'm going to try and convince you that we can violate this condition dynamically with quantum tunneling happening as the universe gets small. So first of all, let's start in a flat spacetime. So I consider in a flat spacetime a physical box, a metal box of side length L at a finite temperature T. So because it's at a finite temperature, if I put a scalar field in here, it's going to be periodic in the inverse temperature. And what about the spatial boundary conditions? Well, actually, what we're going to do is we're going to assume continuous momentum, and we will compactify all of our spatial boundary conditions into an additive Casimir effect, which we'll do at the end, which makes things much easier. So inside this box, I place a regular scalar field, a 5⁴ scalar field, and here's the double L potential with two vacuum states, the blue one, phi2, and the red one, phi1. So as my volume becomes small, my particle will start tunneling between these two vacuum states. So I go from being my entire box being in the blue vacuum state to the red vacuum state and back and forth. So that on average, my equilibrium field theory will have a single minimum, a single vacuum, and in this vacuum, we hope to find that the null energy condition is violated. And this will be the thing that generates our bounce. So to try and show this, we're going to work out the effective action of this effective field theory and then calculate rho plus P in the ground state. So to do this, we're going to use a semi-classical approximation. So what we're going to do is we're going to take the sum over the saddle points with these fluctuation factors to include our one loop fluctuations. And we can do that because we're working in Euclidean time, so we have this minus sign up here. So what are the saddle points? Well, the fun thing about working Euclidean time is that the equation of motion given here effectively describes classical motion of balls rolling around in an upside down potential. So all we have to think about is the possible classical motions you can have of things moving in this potential. So note that we have a source term, but as we set this source term to 0 to do our calculations, this will make our potential effectively degenerate, which means we don't need to consider any spatial saddle points because we know that any of these vacuum bubbles that nucleate will expand to infinity in the degenerate case, as Coleman talked about. So first of all, we have the static saddle points. So these are just particles sitting at the two vacuum states. And then we can look at time-dependent saddle points. And these you can imagine as just literally particles rolling around in your potential. We're going to be interested in low temperature because we don't want thermal symmetry restoration. We're not considering the Gilbert-Zurich mechanism here. And if we consider low temperature, it means the period of my time-dependent saddle points will diverge. So I'm thinking about particles that start here and then roll from one vacuum to the other. And as some of you may know, these are instantons, okay? So here's the plot of the graph. This is over time. As you can see, my particle transitions from the blue vacuum state to the red vacuum state. And importantly, it has to go back because we have to be periodic in time because of our boundary conditions. So we can approximate these as just products of tangent functions. However, we can have multiple transitions happening in a single time period. So we have to consider this gas of instanton and anti-instanton pairs. So here's two, and these are just going to be a product of tangent functions. But also, it doesn't matter when this transition happens. There's this translational invariance. Because if this transition happens at a different point in Euclidean time, it doesn't change the contribution to the partition functions. We have to consider all of them. So you have all of these possible combinations. So this is going to be the full contribution of the instantons to the action. It's going to be this integration over the translational invariance, and you sum over all the possible pairs you can have. So we put this all together, we get our semi-classical approximation of the partition function, which is a contribution from the two static saddle points with these fluctuation factors that we also calculated. And the sum of all the instanton, anti-instanton pairs, and also their fluctuation factors. Okay, so now that we have a partition function, we can go through the usual process of calculating the effective action. So we do the Legendre transformation to describe our action in terms of this single vacuum state of the effective theory, and we get the effective action. So the interesting thing here is three things. One, it is parity even, and two, it is convex, which means there's a single vacuum state at 0, which is exactly what we hoped there would be with this picture. And finally, it's non-extensive. So if we look at this effective action, you can see you've got two terms here. You've got this G0 and G1. These are the tree level and one loop terms. And these are them expressed here. And all these things that are pink are just things that depend non-trivially on extensive variables, the volume and the temperature. And as you can see, it's non-extensive, right? Because it depends very non-trivially on the volume and the temperature, or the inverse temperature 1 over beta. So this is the plot. It's exactly what we hoped it would look like. Indeed, there's just this single vacuum state here. So what we can do is we can calculate rho plus p in this vacuum state. And when we do it for low temperatures, we get this. And what you see here is you have this positive term here, which is comes from thermal fluctuations. And you have a negative term here, which depends on the action of the instantons, which is due to tunneling. And these two things directly compete with each other. And the idea is that for any finite volume, as long as this is a finite volume at a sufficiently low temperature, you will have rho plus p less than 0, and you violate the null energy condition. You also see that at 0 temperature and infinite volume, you get exactly rho plus p equals 0, which as you'd expect. Okay, so this is great, but if we want to talk about some cosmology, we need to do this on a curved background. So what we need to do is we need to upgrade our volume to an FLRW co-moving volume, where the length is going to be multiplied by this scale factor. And if we assume an adiabatic expansion, then effectively all we have to do is we can hold this as being constant in the calculations. So all we have to do is just replace all of our volume factors with an a cubed times the volume factor. Okay, but maybe this isn't so convincing. So luckily, Jean-Alexandre and Sylvia Pla redid this calculation starting from the very beginning with this FLRW background and doing the proper cube thinker spacetime calculations, and indeed they get this result. So at the top, this is what we found in the flat spacetime, and in this FLRW spacetime, you just have these scale factors in here. And the point of this is that if you now take this fluid, this effective theory, and you put it into the Friedmann equations, this is what you get. So here's a plot, and the point here is that if you start here with an initially contracting universe, then your universe will transition into an expanding one due to this tunneling effect that dynamically switches on. So there's a couple of different colors here, and all this means is that basically the blue line here means you have more neck violation, and as you can see, your transition happens quicker, and like down here in the green, you have less neck violation, so it takes slightly longer to have this transition. So, okay, what about these discrete momentum corrections? Well, so what we had to do is we actually assume a continuous momentum, but really we want to have discrete momentum because we work in a finite volume. But indeed, the difference between having discrete momentum and continuous momentum is just the Casimir effect. So what we can do is we can just add a Casimir energy to rho plus p to correct for the fact that we're using continuous momentum. And this is the Casimir effect in a number of different geometries. So if we just consider something like metal plates, as you can see, these are all asymptotic results for large scales. The Casimir effect, it goes like e to minus the length scale, exponential of the negative the length scale. For a periodic box, it's the same. And for a three-sphere, radius of curvature r is again the exponential of minus the length scale. And this is probably going to be the interesting one if you want to do some cosmology inside using your three-sphere as your compact geometry. So when you combine these together, something you'll notice is that this Casimir effect goes like, as we saw, it goes like the length scale, exponential length scale, whereas a tunneling effect goes like the exponential of the volume. This is the instanton action, which depends on the volume. So actually, you have to get down to very, very small length scales, approximately the de Broglie length scale of your particle, for these two things to actually be able to directly compete with each other. Okay, so just to conclude, so the point is that we showed that you can get dynamical neck violation using tunneling at a finite temperature, and that this neck violation will occur for sufficiently low temperatures, as long as you're at a finite volume. So we then use this to show that tunneling in a FLRW volume can dynamically generate this cosmological bounce, and that actually you need to use this Casimir effect contribution to approximate, to account for this approximation we made, and that this effect actually competes with the tunneling effect on these de Broglie length scales. Thank you.
Okay, time for questions. Don't be shy.
Thank you. So, and a very nice talk. Yes. So, and do you have any comment about thermodynamical interpretation of non-extensivity of the effective action?
So you said thermal?
Thermodynamics, right? So,
Okay.
yeah. So, effective action is some kind of free energy, right? So, but you get non-extensive quantity.
Yeah.
So, do you have any comment about that?
Yeah, I mean, so this non-extensive nature really comes from the fact you have this competition of different saddle points, right? So it kind of really comes back to this original picture, the fact that you have these, you have direct competition between these two saddle points, and this gives you some volume dependence, because you have this direct competition, which is due to tunneling, which depends on the volume. So when you work out rho plus p, right? So rho plus p is given. So the rho is, one's given by just a fraction of the volume, and one is the derivative with respect to the volume. Because this depends non-trivially on the volume because of the competition of the different saddle points, that's what gives you this non-extensive nature.
In some sense, entanglement may break down the extensivity.
Okay, I don't know. Okay, thank you.
Because tunneling is a result of the percentage.
Yes.
Right?
Yeah.
So in that sense, this is just my.
Okay, okay, thank you. Yes?
Okay.
So yeah, so I believe that your calculations are correct. If you assume averaging of all of these configurations,
Yeah.
but if these configurations, some of them are macroscopic, you would expect that you know that you will get a violation of if you have a nucleation event, you have a violation of translation invariance or in time or in space. And did you ever think how to include that into the effect?
So you're asking if we should include like spatially dependent saddle points because of if you have bubble nucleation?
For example, yeah.
Yeah. So in this case, we don't have any bubble nucleation because we have degenerate vacuum states. So you don't. So any of your bubbles that nucleate in the limit when you become degenerate, these become infinitely large. So if you consider a finite volume, then your phase transitions happen homogeneously everywhere in your box.
So you don't have violation of homogeneity?
No.
Okay, thanks.
Okay, let's thank the speaker again.